this is also a very important diagram. That is, what if we are constructing two buildings at a very close space distance. So we should always keep a minimum distance between these two buildings, so that in earthquakes these two buildings does not get strike into each other. So thus when a designer is compelled to build a close to an adjacent wall building, so there is need to recognize the actual lateral displacement of each building. So building, if we are considering the building of same overall height, we can see that these two structures can get pounded onto each other in case of earthquake forces. So here you can see that this building come into this and this building come into this. So this after implying this, crossing over is a very dangerous thing. Here also you can see that the buildings are crossing over. After that, what is the effect of soil on the structure? The soil has a very major effect on the structure behavior. Building with isolated footing perform poorly, especially in high seismic zone, and columns and the building are close to being hinged in the flexible soil. So here you can see this is the medium soil behavior, this is the rock behavior. So here you can see that the building sways like this, and here you can see that there is a fixity, so the building sways like this. And on the flexible soil, the medium soil and stiff soil, the behavior is different. So basically soil also has a very important effect on the structure. The stiffer the soil is, or the more the bearing capacity of the soil, the more fixity it will provide on the foundation level. Basically there is also a very important concept that we should understand, the material non-linearity. So some structural damage is allowed during strong earthquake shaking, as I had discussed earlier. So this implies that non-linearity will arise in the overall response of the building. And this test-in curve may be non-linear and also elastic, whereby unloading the material tries to retrace the original path. So structural steel has a definitely yield behavior, and it will not ever retrace its original path when unloaded after yielding. Steel shows the inelastic response to the high intensity earthquakes. So when an inelastic material is subjected to reverse cyclic loading, that is, for example, if earthquake forces strikes on the beam, and when after the removal of earthquake forces tries to come back, so hysteresis takes place in that case, and the material under implied loading absorbs or dissipates energy. So reinforced concrete and structural steel are candidate material for inelastic behavior. And inelastic behavior is basically basis for the second two of the four virtues of earthquake resistant building, that is strength and ductility. After that we should understand the strong column weak beam concept. That is the golden rule of the earthquake resistant buildings. That is, the columns that we are providing should be strong and the beams that we are providing should be weak, and structural elements that are supporting are required to be stronger than those that are being supported by them. That is, column has to be stronger by the beam, and connection should be made stronger than the column members below it. So the items that needs to be checked in earthquake resistant buildings are: beam should be stronger than adjoining braces, beam column joint should be stronger than the adjoining beams, column should be stronger than the adjoining beams, beam column joint should be stronger than the adjoining columns, and foundation should be stronger than the adjoining columns, and soil strata underneath the foundation shall be stronger than the foundation. So basically what happens is that earthquake energy is dissipated uniformly throughout the entire building, rather being concentrated in the one flow. So the total energy absorbed by the whole buildings become large and of ductile type, and the building may be saved from the brittle collapse. Here below you can see that in the case of the first example, the damage is done only on the one story, but in the second example all the columns are standing there only, but the beams are yielding. So damage is distributed on all the stories. So desirable mechanism under earthquake is this one, not this one that we had seen here. So basically what will happen here is that the hinges will form on the end of the beam column junctions, but due to high strength of the column will remain in its place only. So good ductility is achieved in a building when the collapse mechanism is of the desirable type. After that, desirable mechanism under earthquake sway mechanism. So in such a case, the hysteresis loop of its loop deformation curve is stable and full. So these type of hysterical loops imply good energy dissipation in the building throughout each of the elastic hinges at the beam ends. So such a behavior is observed in the building that fails in the sway mechanism. So basically what is a sway mechanism? So buildings that fall in the story mechanism, damages are considered in the columns, and that is not desirable. So when weak column, strong beam concept is applied in the building, as you can see here, that is, the beams are stronger and the columns are weak. This type of behavior is not at all desirable, and story mechanism occur here. But in this type of behavior, that is when the columns are strong and the beams are weak, here you can see that under the effect of H, the delta is very high, and this is a desirable mechanism. But in this story mechanism, you can see that the delta is also very less for the very small delta only. This is the hinge formation in the case of strong column weak beam, and this is the hinge formation in weak column strong beam. So here you can see that all the hinges are formed in the columns, and here you can see that all the hinges are formed in the beams, except some 2 or 3 areas where the hinges are formed in the column. So this is a very desirable mechanism. This is a very strongly rejected or very undesirable mechanism. There can be strength discontinuity in the elevation also. So what is basically strength discontinuity? What we basically do is that sometimes we remove the brick wall from 1 or 2 floors here. So here you can see that we had removed the brick wall from here and here. So this discontinuity causes large inelastic demands at the junctions, and performance during past earthquakes has shown that how sudden a change in this configuration may lead to concentration of ductile demands in a few areas only. So here you can see that this building fails from the bottommost story. After that, we need to understand what is basically short column effect. Short column effect is a very dangerous effect that we as a designer should always take care while designing the structures. The short column effect arises when the column in an RCC frame building is restricted from moving or sliding owing to any restriction, that is this unenforced masonry infill. So all the damage shall be concentrated in this area only. The short column effect can be arise, for example, from sloping ground area when the basement columns are shorter than the others, or like presence of a mezzanine slab, or by the presence of the K bracing, or by the presence of staircase also, or by the presence of plinth beam. After we come back again to ductility. Basically, what was the ductility? Ductility is the capacity to accommodate large lateral deformation along the height. So it is quantified as the ratio mu of the maximum deformation that can be sustained just prior to the collapse.